Welcome to the lecture on Masonry Theory. After this lecture, you will understand which material properties of masonry are important during earthquakes. In many Dutch buildings, the construction material masonry has been used. Although masonry is much appreciated for its aesthetic quality, we face some difficulties because describing and predicting the behavior of this material during earthquakes is rather complex. In this lecture and in the next one, we will discuss how we are improving the reliability of calculation models. We will do this by testing real masonry structures in our lab and comparing the outcomes with computer model predictions. In a minute, we will focus on masonry and its particular challenges. Masonry is a material that is different from, for example, concrete and steel, in the way it responds to seismic loads. But first, let's now refresh some basics of seismic engineering. Inertia forces are those forces that are described by Newton's second law. The sum of forces on an object are equal to the mass of that object multiplied with the acceleration of that object. This may sound a bit abstract, but still I'm sure you all have experienced this effect in public transportation. Look at the image here. Sometimes you're not so lucky to have a seat in public transportation. If the bus or train suddenly brakes, accelerates or changes direction, it is quite a challenge to stay on your feet. The mass of your body has to be kept in place by a force through your feet and your arm. During an earthquake, a masonry house actually faces similar difficulties. The underground and the foundation are accelerating while the mass of the house wants to remain in place. This results in various forces in and on the structure. And let's now have a look at what this means for a typical Dutch house. A typical Dutch terraced house consists of 2 stories and an attic under a tiled roof. Floors are generally made of timber or concrete. The load-bearing walls, especially those in the houses built before the Second World War, are often made out of masonry. In the front and back facade, large window openings are present to let in daylight and fresh air and give access to the house and the backyard. The mass is mainly concentrated in roof tiles, masonry and floors. The masonry structure will have to withstand the forces during earthquakes, according to Newton's second law. The higher the acceleration, the higher the mass, the higher the forces are. How does masonry deal with these forces? To answer this question, let's consider the material in more detail. As you know, masonry consists of bricks that are glued together with mortar. The horizontal mortar connections are called bed joints, and the vertical ones are the head joints. In the Netherlands, many various brick patterns can be found. The most common one is shown here, the so-called running bond. Modeling the combined behavior of the different materials that masonry consists of is particularly challenging. Apart from the strength, one of the important characteristics during an earthquake is the ductility. As explained earlier in lecture 3.1, ductility defines the ability of a structure to sustain large deformations with a high proportion of initial strength and the capacity to absorb energy without failure. In other words, the more ductile, the safer the material is during earthquakes. In the graph here, you can see the stress level that various building materials can take in megapascal on the vertical axis. The steeper the lines, the stiffer the materials. The higher the line reaches, the stronger the materials, the more to the right the line reach, the more deformation is achievable. We call this deformation strain. Regular construction steel, for example, S355, will yield at a stress level of 355 megapascal. On the horizontal axis you can read the accompanying strains in promille. For example, steel S355 has a yield strain of approximately 2 promille. The final fracture will occur beyond 20 promille making steel a very ductile material. Now the red line represents masonry. Compared to steel, you can see it's not really strong and stiff, so the height of the peak stress and the slope of the diagram are both rather limited. The peak stress is at approximately between 10 and 20 megapascal for good Dutch masonry, while the strain at the peak is about 5 promille. The behavior before and after the peak is very different for each type of masonry, as we can see here for a collection of horizontal compression tests on Groningen masonry samples. Some masonries are very brittle, others are rather ductile, and unlike construction steel, masonry is and was manufactured with a very wide range of mortar and brick qualities. Therefore, laboratory tests will have to be carried out for each type of masonry to determine its specific mechanical properties. In the material diagram from these examples, a gradual increase in loading is assumed, going stepwise from a small load to failure load in compression. And this brings us to a further complication. A house that is accelerating due to an earthquake will not deform only once, but back and forth, sometimes even during several seconds or minutes. Determining and predicting this cyclic behavior of masonry adds another difficulty. We need laboratory tests and computer models with cyclic loading. In this animation, you can see both the cyclic character and the different directions of deformations. With the earthquake in the animation, the front facade of the house is loaded in plane, while the left and right facades are loaded out of plane. Let's look at these deformations in closer detail. Firstly, we have out-of-plane deformation. During out-of-plane deformation, the wall is loaded in a direction perpendicular to the plane in which the wall lays, as indicated here with the green cross-section. Secondly, we have in-plane deformation. The wall is now loaded in parallel to its own plane, as shown with the green section. Three types of in-plane deformation are distinguished, namely tension, shearing and compression. Let's look at all types of forces and how these forces are related to material properties of the masonry. Tension forces applied to masonry in the vertical direction as shown typically lead to exceeding the maximum bond stress between brick and mortar. This will generally result in an almost horizontal crack. Tension forces applied to masonry in the horizontal direction as shown typically lead to exceeding the maximum bond stress between brick and mortar, and this will result in an almost vertical crack, sometimes going through the bricks and sometimes through the head joints. Shear action is illustrated in the image here. We see that horizontal forces in opposite directions lead to the sliding of brick layers. The way this sliding occurs is very much depending on the boundary conditions. If, for example, a vertical force is compressing the layers, sliding will become more difficult than without this vertical force. Also, other variations of shear damage can be found, but we will show some examples of this in lecture 6.2. As we have seen in the material properties, the compressive strength of masonry is between 10 and 20 megapascal for the better qualities of masonry. If the vertical stress on the masonry exceeds this level, the masonry will be crushed either in the bed joints or in the bricks, depending on which of the two is the least strong. During earthquakes, this crushing occurs quite often in those corners of walls that have to deal with large concentrated compressive forces on a very small area. Compression can also occur in horizontal direction, although generally the self-weight of the construction leads to a situation in which the vertical compressive loads are governing. In the out-of-plane direction, the wall is loaded by its own mass during an earthquake. If the movement is restricted in the top and in the bottom, bending may occur. Here you can see an example of deflection of a wall out of plane. In the image here, the left side of the wall is compressed, whereas the right side of the wall is stretched. and this bending action can lead to horizontal cracks, as shown here. So, in this lecture we have seen how masonry can respond to earthquake accelerations. We learned that this response can be divided in in-plane and out-of-plane direction, and various material properties needs to be determined in order to predict the safety. In the next lecture we will see some of the experiments used for this determination. Thank you for your attention.